Okay, so good afternoon, everyone. It is really a great pleasure that I was invited to this excellent meeting, and my sincerest apologies for not being able to be there, but I have teaching responsibilities that I cannot ignore right now. So thank you, Shadab, and all the organizers for giving me this opportunity to talk to you about the work that we have been doing in trying to understand early galaxies and what they mean in the epoch of reionization. So I think what I'll try and do today is give you a global overview of what has been happening in the field, especially in terms of the data that we have been getting from the James Webb Space Telescope. So just to put this into perspective, the era that I'm going to be talking about today is this epoch of reionization, which started when the first galaxies started forming in the universe at a redshift of 30 or 13, depending on really your favorite model for forming the first galaxies and the first stars. The moment these first sources turned on, they started producing the first photons that could break up the hydrogen surrounding them back into electrons and protons. This marks the rise of the epoch of reionization. So you can see here, we showed the epoch of reionization by these gray shaded regions around galaxies. So these are the ionized regions that galaxies are building around themselves. As time goes by, more and more galaxies form, these regions start growing and overlapping until at some point, these ionized regions cover all of the available volume of the universe. And at this point, we say that the epoch of reionization is complete. We think this happened somewhere within the first billion years of the universe. But what is really crucial to note is that this was the last major phase transition of all of the hydrogen in the universe. Once the epoch of reionization was complete, since then, all of the hydrogen in the universe has remained reionized for the next 12.5 billion years. So what I'll try and do today is give you an idea of how we are going to probe this epoch, what are the sorts of sources we are expecting to detect as we go on. And I would just like to acknowledge the team in Groningen. So these are all of the young people who are taking the lead in most of the work that I'm showing you today. And we are, of course, involved in a number of different experiments, including the SKA, Euclid, ALMA, and also James Webb. And I would especially like to give a huge amount of thanks to Atri Chatterjee and Tirthankar Choudhury, who were two of my really excellent collaborators and have led a lot of this work that I'm going to be showing you. Okay, so let me just start by saying that over the past decade, we have had a number of fantastic observatories ranging from Subaru, the Very Large Telescope, Spitzer, HST, the Atacama Large Millimeter Array, and finally the James Webb, which have allowed us to build a huge amount of statistics on galaxies in the first billion years. So this is really the golden age for observing early galaxies, because now we are able to collect statistics ranging from the luminosity functions all the way up to a redshift of 20, as I'm going to just show you in a minute. So this is just how many galaxies do you have per co-moving megaparsec as a function of their luminosity, so the luminosity function. How much total star formation rate do you have as a function of per co-moving volume of the universe? So this is the star formation rate density. How much mass do you have bound in stars per co-moving volume of space, which is the stellar mass density? And of course, something that we are really interested in is what are the properties in terms of the dust masses and metallicities of these early sources. And finally, with ALMA and James Webb, what we are able to do for the first time ever is actually look at the sizes and even mergers in early galaxies, even up to a redshift of 11. And with lensing, we are even able to probe things which are really young star clusters. So these are really, really tiny objects that for the first time we are able to see, given the resolution and the sensitivity of telescopes such as the James Webb. So this is just to give you an idea of the amount of statistics that we have been able to collect to build a coherent view of galaxy formation in the first billion years. Now, of course, this amazing amount of data that we have has led to a huge number of open questions ranging from, so what were the physical properties of these early galaxies, especially in terms of metals and dust, how dusty or how metal rich were these objects? How was the environment actually affecting the assembly of early galaxies? How did these galaxies evolve through cosmic time? When and how was the universe reionized, which were the key sources of reionization, and what was the impact of reionization on galaxy formation? As we probe to higher and higher redshifts, we are beginning to detect objects which look like black holes even out to redshifts of 10. So of course, this necessitates the question of what was the role of black holes in early galaxy formation and reionization? Naturally, this leads us to ask, so how many gravitational wave events do we actually expect from the high redshift universe? And something that I'm not going to talk about at all today, but if you're interested, please do ask me more about this, is how can we actually probe cosmology using these early sources? So this, I mean, in terms of what can galaxy formation and these high redshifts tell us about the nature of dark matter, especially in terms of the nature of warm dark matter. So we are using a huge amount of data from ALMA and James Webb to really pin down or baseline theoretical models as we look forward to making predictions for the era of Euclid, SKA, and of course, LISA. So I think the whole purpose of this meeting is to really talk about all these large surveys, of which Euclid, SKA, and LISA are definitely going to be the forerunners. So what I would like to talk to you about today is, sorry, just 1 second, sorry. I am really, really sorry, but, oh wait, sorry, my Zoom crashed, just 1 second. Okay, sorry. I'm really sorry, my PowerPoint just decided to crash. Okay, good. Okay, so I just raised a lot of these open questions. And so, of course, the complexity of this problem really necessitates a number of different modeling techniques. So there has been a huge amount of effort trying to model galaxies in the first billion years. And so this is something we tried to compile in our review article in 2018. This is already completely out of date. So there are a number of simulations listed here below, which we have completely missed because they were produced after we wrote this review. But this is just to give you an idea that there is a huge amount of work which has been done in trying to model galaxy formation on really small scale. So this is really trying to look at the physical properties of early galaxy populations. We have intermediate scale models, which are on the scales of a few tens to a few hundred megaparsec, where people are trying to model galaxy formation and reionization, but these scales are not large enough to capture the large scale reionization process. So we don't reach convergence on the history and the topology of reionization. To this end, a number of large scale models have been developed, which are looking at scales of hundreds of megaparsecs, but these do not model galaxy formation. And so to fill this void, to really connect the process of galaxy formation with reionization, we have produced a model which we call Astreus, and I'm just going to talk to you about this in a minute. Before I jump into the model, let me just show you what are the key problems that we are facing when we are trying to model this interplay between galaxy formation and reionization. So really, at the really zeroth level, when we try and model reionization, what we are trying to model is the fractional volume of the universe, which is filled with ionized hydrogen. As you can imagine, this is driven by a source term. So the first part of the source term is how many ionizing photons are sources able to produce per co-moving volume of space. So this is this nth term. The second term is the escape fraction. We know galaxies are really complicated systems, and so only a small fraction of the ionizing photons that are produced within a source can actually come out of the source. So these two terms together comprise our source term. We also have a recombination term, which is driven by the fact that when you have galaxies in extremely dense regions, once you ionize these regions, they can actually recombine on short time scale, so you have to reionize them multiple times. However, for the purposes of this talk, I'm completely going to ignore this recombination term, and I'm only going to talk about the source term. So let me show you the source population. So this is just the luminosity function, so the number density of objects per co-moving megaparsec as a function of the UV magnitude. So just to remind everybody, minus 14, etc. These are really faint objects. As we go towards this other range, which is minus 24, minus 25, these are really, really bright sources. And I'm showing you the luminosity functions going from a redshift from about 7 to a redshift as high as 20. Everything that you see above a redshift of 12, so these last few panels are the most recent results that we have from the James Webb Space Telescope. So now the issue is the following. As you can clearly see, the lowest mass or the lowest luminosity sources are the most numerous, so we think they should have a significant contribution to reionization. But we are only able to probe them reasonably up to a redshift of about 8 or so. As we go to even higher redshifts, these things are so tiny, they are so faint that we really need dedicated surveys with the James Webb to really probe this faint end of the luminosity function. So this is something that is really ongoing as we speak. So this is the first problem. How far down in luminosity can galaxies actually keep forming stars? Because this is really going to determine how many ionizing photons do we actually produce at these high redshifts. A similar problem exists when you look at really, really massive, rare, and bright objects. So here, for example, what I'm showing you is the data at redshift 13, even up to a redshift of 20. These things are enormously bright. So these are really highly biased peaks where star formation is taking place. But the key problem that we are facing, and you might have been hearing about this a lot, is the fact that these galaxies seem too many for their number density at these high redshifts. So what you expect is the solid blue line. But as you can see, these objects are really lying orders of magnitude above what theory is predicting. And indeed, these objects are actually sometimes they are more compatible with a scenario in which all of your halos have a gas mass, which is linked to the dark matter mass through the cosmological ratio. So really the maximum gas mass any halo can have. And all of this gas turns into stars instantaneously. So we are really pushing the physical bounds of what is possible in order to explain these sources. And so the point that I would like to make is that we really need large surveys to confirm both the nature of these objects. So are they, for example, star-forming galaxies, or are they really black holes that we are looking at really in the early epochs of the universe? And we also need to confirm whether these are at the right redshifts. So this is something that is ongoing as we speak with James Webb. People are trying to target these individual sources to really confirm what are they as we go to these high redshifts. So essentially what is happening is that as we go to redshifts above 12 or so, the source population for reionization, so whether these are star-forming galaxies, black holes, and how many do we have at any given epoch is really an open question. If you remember, the second part of the source term is how many ionizing photons can actually come out of these galaxies as a function of redshift. All the points that you see of a given color are from the same group, so they are targeting really similar sources. And what you can clearly see here is that there is, as of now, there is no consensus on how the escape fraction evolves, even as a function of redshift. I have not yet started to even break this into as a function of mass, as a function of galaxy properties. So the escape fraction really remains a key outstanding problem. So both the source population and the escape fraction are key outstanding problems in the field of early galaxy formation. So to try and address these problems, what we have done is we built this really large numerical simulation, which we call ASTRAEUS, which is a semi-numerical coupling of galaxy formation and reionization in n-body dark matter simulation. So we have a hybrid approach where we have extremely large dark matter simulations. So this is 230 megaparsec simulations with 3,840 cube particles. So we can go down in terms of mass to 10 to the 8 solar mass halos to be able to capture those tiny early galaxies that were forming at high redshifts. At each redshift, this is combined with a galaxy formation model, which we call Delphi. Using the properties of those sources, using whatever assumptions on the escape fraction, we generate our reionization fields. So this is really a three-step process in which we are coupling n-body simulations with galaxy formation with radiative transfer. And the results have been published in a number of works where we have tried to look at galaxy formation, the effect on reionization feedback, star formation histories, metallicity relations, black holes, and now also looking at these things called Lyman alpha emitters, which I'm going to talk about in a second. For everybody who is interested, what I would like for you to note is that we have all the key physical processes of galaxy formation, including star formation, supernova feedback, black hole seeding, growth, reionization feedback, for which we use many different prescriptions. We study many different prescriptions for the escape fraction because, as I said, this is really an open problem. And we include prescriptions for chemical enrichment and dust. And so this is just a schematic showing you how these galaxy assemblies actually look like. So we start at high redshifts with low mass objects, which are merging through time to form larger and larger objects. And each of these halos, each of these progenitor halos, is color-coded by the star formation rate. So at every point in the history of a galaxy, you can see how it was building up its mass, how it was building up its metals and its dust component. So let me just show you one key result. So here what I'm showing you is the density fields, the reionization fields, the stellar mass function, which is just how much stellar mass do you have per co-moving volume. And the UV luminosity function, again, how many galaxies do you have as a function of the UV magnitude or UV luminosity. And what we have tried to do is, because we have these large simulations, we can actually start to simulate different fields of view. So for example, the smallest box that you see here, the orange box, is what the James Webb Deep Fields are going to see. The greenish box is what the medium fields are going to see. And the blue box is the field of view of the Nancy Grace Roman Space Telescope, which used to be called WFIRST. So what I'm showing you here is the stellar mass functions and luminosity functions color-coded by the underlying density in which galaxies are sitting. So the first thing that you can clearly see here is, let me just focus on the luminosity function. The shape of the luminosity function is quite independent of the environmental density, but it will severely determine the exact amplitude that you measure for the luminosity function. And so when we are looking at James Webb type of fields of views, we have to be really, really careful in linking this to the underlying density before we can actually get an idea of what the actual amplitude is. Or alternatively, we can use the amplitude to get an idea of the underlying overdensity. But what this already tells you is that the properties of galaxies are really going to be dependent on the kind of environment in which they are sitting. This brings me to the idea of, okay, so, you know, we said reionization is driven by the source population. One really critical parameter is, so we model our source population, and the second key parameter, which we were discussing about, was this escape fraction. So our model is really flexible, and so we have run it for many different kinds of escape fractions. So let me just show you what happens for two different models. So the model that I'm showing here shows the evolution of reionization from a redshift of 10 down to a redshift of about 6.5. All of the blue patches that you see are the reionized patches. In this sort of a scenario, the escape fraction decreases with increasing mass. So low mass galaxies are providing the bulk of reionizing photons. So what you can see here is that in this sort of a situation, the distribution of ionized regions is quite homogeneous because low mass galaxies are homogeneously distributed. And so your ionized regions are kind of unbiased in a certain way. Contrast this to the lower panel, where now the escape fraction increases as a function of mass. So high mass galaxies can input a larger number of ionizing photons for reionization. What you can immediately start to see is, for example, if I look at a redshift of about 8, you can really start to see that the reionization topology is much more biased when high mass galaxies are providing the bulk of reionizing photons. And it is just because of the underlying bias in the distribution of high mass galaxies. So now, of course, the question is, yes, well, how would you actually test this? So this brings me to the idea of testing the topology of reionization with a class of galaxies called Lyman alpha emitters, which are viewed through their Lyman alpha emission line at 1216 angstrom in the rest frame of the galaxy. So the idea is really simple. If you have galaxies which are embedded in ionized regions, if these regions are sufficiently large, the Lyman alpha, as it goes out from the galaxy, gets redshifted. And so some or all of these galaxies can be visible as Lyman alpha emitters. Galaxies which have small or no ionized regions will basically just get all of their Lyman alpha scattered away. And so in the initial stages of reionization, only highly clustered galaxies will be visible as Lyman alpha emitters, with more and more normal galaxies or field galaxies becoming visible in Lyman alpha as reionization proceeds. So this is something that we have already tested as early as 2016, where we found these two really bright Lyman alpha emitters at a redshift of 7. We made the prediction that these were actually clustered with a lot of faint star-forming galaxies, an idea that we could actually verify with observations from the Hubble Space Telescope. So this is the number of clustering objects as a function of the wideband magnitude. What we predicted was the green line, that these two galaxies had tens of objects distributed around them, which were contributing to building an ionized region. What we found was the reddish histogram. So indeed, there are a lot of low mass, faint galaxies which are clustered, making these galaxies visible in the Lyman alpha. What you would have expected if these galaxies were not clustered at all is this blackish histogram, so about one galaxy around them. So this was one of the first observational evidences that clustered galaxies are preferentially visible in terms of their Lyman alpha emission. Now, the issue is that actually the visibility of galaxies in Lyman alpha is significantly affected by the escape fraction. So again, I'm showing you are the same model that I showed you before, Astreas. Again, in the top panel, this is if the escape fraction decreases with an increase in mass. Lower panel is escape fraction increases with an increase in mass. What you can clearly see is, not only is the topology of reionization different, but the distribution and the luminosity of galaxies you would call Lyman alpha emitters is also different. And so, although it's a really tiny parameter, it is actually going to affect what we call a Lyman alpha emitter. And so this now you may ask, well, why do we actually care? The reason we care is that as we look towards the future, as we look towards SKA and Euclid, what we are really aiming to do is to synergize the data from these different instruments, where the SKA is going to give us the 21 centimeter emission from neutral hydrogen. And the idea is to cross-correlate this with the galaxy population that you get from large surveys, including Nancy Grace or Euclid, even Subaru, to try and get a complete picture, not just of reionization, but the sources that are actually driving this process. So this is something which I'm leading as a co-lead for the SKA Synergy Group and the Euclid Theory Working Group. And just to give you an idea, the key trend that we are expecting to see is this is the 21 centimeter Lyman alpha correlation as a function of scale. What we are expecting is that the correlation will be negative because wherever you have neutral hydrogen, by definition, you will not have Lyman alpha emitters. The amplitude of this correlation will be the strongest when the universe is half neutral, half ionized, because here you have enough galaxies visible in Lyman alpha, but you also have a lot of power in 21 centimeter. As the universe becomes more and more ionized, more galaxies are visible as Lyman alpha emitters, but now the power in 21 centimeter drops off exponentially. And so this is the sort of trend that you can use to really distinguish, to really put constraints on the patchy progress of reionization. And the scale at which you see this turnover, this actually tells you something about the typical bubble size, which is being occupied by Lyman alpha emitters. And just to sort of end this, we have tried to look at what kind of survey parameters do we actually need to maximize these sort of 21 centimeter Lyman alpha correlations. And I would just like for you to focus on the fact that as the volume decreases, the thermal noise increases. As the number of Lyman alpha emitters decreases, the short noise increases. And so we have been trying to find optimal strategies to maximize this correlation. And what we are finding is that if we want to target intermediate luminosity Lyman alpha emitters, so about 10 to the 42, 10 to the 43 ergs per second, we need to look at fields of view which are roughly of the order of 25 degrees squared. So these are extremely large fields of views, but very much doable with Nancy Grace or with the Silver Rush kind of surveys. Of course, you can always go to smaller volumes, but then you would have to probe even fainter Lyman alpha emitters. I'm not going to talk about AGN contribution, just to, in the interest of time, what I would like to do is just leave you with this sort of advances and implications end slide, where we have a number of fantastic instruments that are going to produce enormous amounts of data. These are going to tell us a lot about the global properties of galaxy populations. They are also going to shed light on individual galaxy properties, as we have already seen from the dust masses, stellar masses that we are getting from ALMA. 21 centimeter cosmology will be an enormously important resource to really get constraints on the source population, on the patchiness, on the progress of reionization. And of course, all of this is going to give us enough information to be able to make predictions about the black hole population at high redshift, which is something that is going to be extremely crucial for LISA to try and detect how many black holes do we actually have at high redshifts and how many mergers do we actually expect. And I would just like to leave you with the fact that there is a Euclid theory work package and there is an SKA synergy working group where we are really trying to synergize different instruments to try and make links between instruments, including Euclid, ALMA, LISA, SKA. We're trying to organize test campaigns, data challenges, and everybody is most welcome to join these. So if you're interested, please mail any of us. So the coordinators for both the Euclid and SKA are listed here. And I would just like to really stress that we are really looking for people to help us in this endeavor. So if you are at all interested, then please do get in touch. And I would like to end here. Thank you.
Questions Hi, Pratika. I had a question.
Hello.
Yeah, you showed that the Lyman alpha emitters, the luminosity depends on the reionization topology, I mean, which was determined by the escape fraction. So basically, I mean, which effects played the most dominant role in kind of deciding the luminosity of the Lyman alpha emitters?
Yeah. It's such a nice question. So, the first thing is just that the nebula emission scales as 1 minus F escape. So if your F escape is higher or lower, it really changes the intrinsic luminosity that you can produce in any of your nebula emission lines. And the second thing is that if you look at the top and the bottom panels, the distribution of ionized regions is really different. So for example, if you have low mass galaxies sitting in one of these two different situations along different lines of sight, the transmission of Lyman alpha can be really different. So I would say it's both these effects together, that the escape fraction affects both the intrinsic luminosity and the line of sight transmission. And so what we are finding is that for different scenarios of the escape fraction, the Lyman alpha luminosity functions actually start to look really different. So a galaxy could still be visible as a Lyman alpha emitter. The same galaxy could be a Lyman alpha emitter in different F escape scenarios, but its luminosity could be really different. Sorry, does this sort of answer your question?
Yeah. Thanks. Yeah.
First.
Any other questions? Okay, so let's thank the speaker again.
Thank you very much. Thank you.